The next topic that we want to look at is forced vibrations and resonance. Okay, here we want to talk about something called forced vibrations. And sort of the classic example used is a tuning fork. Now, the thing about a tuning fork that's neat is that if you strike it, it will vibrate at one frequency very strongly. So if you have a tuning fork that's set to vibrate at 440 hertz, it'll vibrate at 440 hertz, and you'll get something that looks like a very nice sine wave. But the other thing about a tuning fork, though, is that if you strike one and you listen to it, the sound is very faint. It's not loud at all. But if you take the bottom of a tuning fork and you press it against the tabletop, the whole tabletop will start to vibrate at that frequency and the sound will get much louder. So the vibrations of the tuning fork are causing the whole table to vibrate, and that creates a greater surface pushing the air, and that's what makes the sound louder. Now, it seems like maybe a little bit of magic. How is it that you can make the sound louder that way? Doesn't that violate conservation of energy? And the answer to that is actually no, because if you strike the tuning fork and you're just holding it loosely in your fingers, it'll vibrate for a long, long time before the sound dies down. But if you hold it against the tabletop, it'll vibrate much louder, but that energy will be used up much more quickly. So you get more sound, but it doesn't last as long. But in any case, what you have with the tuning fork is vibrating back and forth, and when you press it against the tabletop, it causes the tabletop to vibrate back and forth in the same way. And since, of course, the tabletop is a much bigger area, it pushes more air and makes a louder sound. The next thing that we want to talk about is something called resonance, and that has to do with something vibrating at what we call its natural frequency. Now, imagine you have a glass bottle, and you drop it on the floor, and it doesn't crack, something tough like a wine bottle maybe. It doesn't break, but it just kind of bounces, and when it hits, it makes a sound, right? Now, let's assume that at a slightly different time, you drop a pipe wrench on the ground. If you were blindfolded, and I dropped a bottle on the ground, and it hit, and then I dropped the pipe wrench on the ground, and it hit, do you think you'd be able to tell which one was which just by the sound it made? I think pretty much everyone would have to say yes to that. And the reason for that is because the sounds that something makes when it's struck, it makes those sounds because the atoms and molecules of that material are vibrating at the natural frequency of that object. Every object has its own natural characteristic frequency that causes it to make its own distinct sound when it vibrates. And that is called the natural frequency of the object. And sometimes you'll hear it called the resonant frequency of the object. But those are the frequencies at which the thing can naturally vibrate, and it doesn't take a lot of energy to get it vibrating at that frequency. So in the previous example, if I have my tuning fork on the tabletop for illustration purposes, if the tuning fork is vibrating at a frequency that is not the natural frequency of the tabletop can still be made to vibrate at that frequency, but it won't vibrate as loudly, it won't vibrate as well. If, however, you happen to have a tuning fork that just happened to be at just the same frequency as the tabletop's natural frequency, you would get an even louder, dramatically louder sound from that vibration. And so here we can see that forced vibrations and resonance can actually be linked together with one another. Now, here's another application of this idea of forced vibrations and resonance. And the idea is that you have two tuning forks that are the same kind of tuning fork. That is, they both have the same natural frequency. And you strike one, and you start it vibrating. Now, you don't even have to touch the other tuning fork, but shortly thereafter, it'll start vibrating too, at the same frequency. And that's because the first tuning fork is sending out sound waves of that frequency that's this guy's natural frequency. They're the same frequency tuning fork. They have the same natural frequency. So the guy this naturally wants to vibrate at is the same frequency that this guy naturally wants to vibrate at. And so the vibrations from the sound wave come over here, and when they strike this guy, they set it vibrating at its natural frequency. To get the tuning fork vibrating at a different frequency would require a lot more energy. But if you're at the resonant frequency, it doesn't take much energy to make you vibrate. And so the small vibrations produced by this tuning fork can set the second tuning fork in motion. Now, what is it that we mean when we say that something has a natural frequency or that it has a resonance or a resonant frequency? So think about a child on a swing. Now, most of you probably have either been a child on a swing at some point that had someone pushing you, or you've had maybe a niece or a nephew or little brother or little sister that you've pushed on a swing. And if you push a child on a swing, one of the things that is interesting about pendulums, and the swing would certainly be an example of a kind of pendulum. Imagine you have a pendulum here and it's swinging back and forth. And so if you let it go, eventually it'll die down and the string will just be straight up and down. But if you stretch it out and then let it go, it's going to swing back and forth. Now, if I stretch it out a little bit further and let it go back and forth, what's interesting is the time it takes to go back and forth is the same, regardless of how high up you release it from. And so that's one of the reasons why clocks use pendulums, if you've ever seen like an old-timey grandfather clock. Because even if the clock is losing, the clock is dying down and the pendulum is swinging back and forth with less amplitude, it still takes 1 second to vibrate back and forth if a second is what is the time of that pendulum swing. So, no matter how big the child's swing is, it's going to take the same amount of time to go back and forth. That enables you to establish a rhythm. Now, here's the idea. You push the child, and the child swings up, and then the child swings back, and then you push it again. There's a right way and a wrong way to do it. Here, the one with the big red X is showing you the wrong way, and you can see the blue arrows, this arrow showing the guy pushing, and this guy's showing the motion of the swing going back up. And so the idea is this. Normally, the correct way, you push it and the child swings forward and then swings back. You want to wait just until the child stops and then push. That child's going to stop just for a second, and then you push, and it goes up a little bit higher and comes back. Now here, the guy's pushing too soon. The child's still swinging up, and so he's pushing against the child's momentum and slowing the child down rather than his force adding to the motion. Here, when the child stops and you push a little bit more, you're doing a little bit of work to increase the energy, and so the child swings higher and higher with each push. Now, what this has to do with resonance is, because no matter how big the swing is, it takes the same amount of time to go back and forth, there's a rhythm to push the child. You get into a rhythm, so you push at just that rhythm. Push, push, push. If you push at just the right rhythm, every time you push, the child's going to go a little bit higher than it did before. If you push out of that rhythm, you're fighting against the child, and so the work that you do to push is wasted. It's not increasing the energy. It's not increasing the size of the swing. So the key thing, if you have a system that has a natural frequency and you time your pushes so that you're pushing just at the right time so that the energy you add is not wasted, then what you'll find is that you get very big swings for very small amount of pushes. Little bit of energy added on each push, but it leads to really big swings in the motion. In other words, for small amounts of pushing, you can get big increases in the amplitude of the vibration. So here's that tuning fork example again, and this is the second tuning fork. And so the sound is coming in. You can see the sound wave here from the first tuning fork, and here's one of those condensations. The air is bunched up, the pressure is high, and it pushes the tuning fork, and it causes the tine to move over to the right. And then this tine is swinging back, and the sound wave is passed over, and it starts pushing this tine forward. Now, this tine is swinging back, but because over here there's a rarefaction where the air is less dense, this guy's going to overswing a little bit. And you can see this guy is not exactly straight up and down. So when this guy is going this way, this guy's swinging that way a little bit. Now, if you have it timed just right, when this guy swings back to the vertical, it'll be right when this guy arrives, the next condensation. And so this guy, if there was no other sound, this guy would still go back and forth a little bit, wah, 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 like that. But what happens is, so this guy goes forward, it goes back, it overshoots, it's starting to go back. Now, it would overshoot again in the other direction, but right at that time, the second sound wave reinforces it and pushes it a little bit further. And so even though these guys don't have a lot of force, they're very, very tiny, there's enough of them that are reinforcing the motion to make the tuning fork vibrate in a very big swing, relatively speaking. So this guy here starts vibrating, the sound waves come over, and they're at just the right frequency to make this guy start vibrating without even being touched at all by anything other than the air. Now, sometimes resonance can have negative consequences as well. And this is a picture of one of the most famous engineering disasters of the 20th century. It happened in the 1940s. And this is the famous Tacoma Narrows Bridge from Tacoma, Washington. And a few months after the bridge was completed, had its construction completed, there was a long, sustained wind that blew underneath the bridge. And that created this sort of eddy currents, these sort of swirling motion underneath the bridge as it passed under the bridge. And an absolute fluke. There could have been a million days in a row where this never happened, but it just happened on this particular day. The wind was at just the right strength and in just the right direction to create these eddy currents to rock the bridge at its resonant frequency. And so the bridge started vibrating. And just like the child's swing, every time the swirl of the eddy current rocked the bridge, it made it swing a little bit bigger than before. And you can see eventually the bridge collapsed because the swings just got too big for the structure to sustain. I may try to find a video of this disaster to put on canvas for you guys to see, because it's actually pretty spectacular to see this motion of this bridge. And the wind wasn't even that particularly strong that day. It happened to be under the right conditions to make this happen. And again, this is another example of a resonance phenomenon.